Swayam Prabha. Digital India. Educated India.
Hello, welcome to Introduction to Composite Materials. Today is the fourth lecture of the ongoing week, and today we will introduce another lamination sequence, and that particular lamination sequence is known as a sequence for quasi-isotropic laminates. So, that is the theme of our discussion. Quasi-isotropic laminates. This is what we want to discuss today. Now, here the purpose of the discussion or detailed analysis is to somehow figure out a smart way such that the properties of the laminate, not individual layers of the laminate, are similar to that of isotropic materials in the in plane direction, Okay. So, what does that mean? What that means is that if I have a laminate and if I pull the laminate in this direction, or if I pull it in this direction, or if I pull it in this direction, or any direction for all I care about, then the behavior of the laminate should be same as that of an isotropic material. That is what we want to achieve, because if that is the case, then this material laminate will have equal stiffness in all directions, and most likely if it will have equal strength in all directions. So, it will be reliable in terms of its performance regardless whatever direction of load it is facing. Now, this discussion I wanted to again re-emphasize is in context of only in plane response. We are not talking about whether the plate is going to have similar response when it is being bent in different directions. So, when we are talking about quasi-isotropy, we are talking about the behavior of the plate in the in plane direction. Regardless of whichever direction we pull it, it will extend by the same amount. So, that is what the in plane response implies, and that is why we are talking about quasi, and it is quasi because we are only worried about the in plane response. We are not talking about the bending response of the system. Now, if we look at an isotropic plate, let us look at how it, what kind of, so an isotropic plate will also have an A matrix, B matrix, D matrix. Okay. So, if you have a plate and it is made up of isotropic material, excuse me. So, this is, so let us say this is an isotropic plate. You can also generate its A, B and D matrices. Okay. If the plate is of uniform thickness, then its B matrix and the material is homogeneous throughout the thickness, then because there is same material on top and bottom of the mid plane, B matrix for this thing is going to be 0. Okay. And then what about the A matrix? So, the A matrix elements can be defined as Qij times, it is just single layer because it is one single material. So, thickness of the plate, right. And what are the elements for an isotropic material for the Q matrix? So, for isotropy for isotropic materials, let us look at what is the Q matrix. Q is equal to E divided by 1 minus nu square. So, this is something we have discussed earlier, and then the second element is nu E divided by 1 minus nu square, third element is 0, nu E divided by 1 minus nu square, E divided by 1 minus mu square 0, 0, 0 and E divided by 2 times 1 plus Poisson's ratio. So, this is how the Q matrix looks for an isotropic material, and we can use these elements to compute elements of the A matrix for an isotropic plate. So, for isotropic plate, A is nothing as but we just multiply this by the thickness, which is T. So, then we get, so I will just write it down. So, it is E times T divided by 1 minus Poisson square, 1 minus Poisson square, 0, 0, oh there is a T here, E T divided by 1 minus Poisson square, 0, 0, E T divided by 2 times 1 plus mu. So, this is the A matrix for an isotropic plate. What we want is a lamination sequence where the matrix looks something like this, okay. So, so this is an isotropic plate, and suppose there is a composite plate. So, let us say that a composite layer laminate, not layer, is quasi-isotropic. Let us assume that we have put layers in such a way that it is indeed quasi-isotropic, and if it is indeed quasi-isotropic, then A11 for that material will be same as A22. So, if it is indeed quasi-isotropic, then we can say A11 will be same as A22, because that is the condition in isotropic situation, right. So, A11 is same as A22. The other thing we see it is that if we look at A11 minus A12, if we take the difference A11 minus A12, what do we get? We get ET 1 minus nu square times 1 minus nu, and this 1 minus nu cancels out from numerator and denominator. So, it is E t divided by 1 plus nu, and this is nothing but twice of A66, it is twice of A66. So, if there is indeed a quasi-isotropic plate, what we have to ensure is that its A11 should be same as A22, and the difference between A11 and A12 should be twice of A66. And the third thing we have to ensure is that A16 should be 0 and A26 should be 0. Okay. So, these are the requirements. These are the requirements for quasi-isotropy. These are the requirements for quasi-isotropy. So, the question is, what kind of a lamination sequence I have to generate which ensures that A11 is equal to A12. The same lamination sequence should also give me a situation where A11 minus A12 should equal twice of A66 and A16 and A26 should be 0. Okay. So, the question is, what lamination sequence will ensure these conditions? So, people have looked at this question, and if you do some little bit of mathematical analysis, you come up with a answer, and the answer is having 3 parts, okay, actually just 2 parts, and both of them have to be satisfied. First one is number of layers should be more than or equal to 3. That is one. And the second one is that orientation of successive layers should be in steps of pi over n radians. So, number of layers, so n is number of layers, n is number of layers. Okay. So, if you meet these 2 conditions, you will ensure that there is quasi-isotropy and the plate will behave as a quasi-isotropic material in the in plane direction. Out of plane, we still have to worry about it, but in plane it will ensure that. So, examples. Okay. Case 1, you can have first layer at 0 degree. So, minimum number of layers should be 3. So, it will have 0, then the second layer could be at 60 degrees and the third layer could be at 120 degrees, or you can also call it as minus 60 degrees. 120 is same as minus 60. Okay. So, you can have a 3 layer laminate, first layer 0, 60, minus 60. Okay. First layer is 0, 60 and minus 60, and when you do this, it will ensure that, so for this lamination sequence these conditions will be satisfied. A16 and A26 will be 0 because you have 60 and minus 60, and when you do all the calculations you will find out that A11 minus A12 will be equal to twice of A66, it will actually work out. Okay. But a problem with this lamination sequence is that it is not symmetric. So, B will be non-zero. So, you can have another example. So, you can have 0, 60, minus 60, minus 60, 60, 0. So, this is essentially 0, 60, minus 60 symmetric, and in this case B will be also 0 and it will still be quasi-isotropic, because A matrix only depends on the thicknesses, A matrix only depends on thicknesses. So, the same sequence is being repeated, so the quasi-isotropic will be retained. The other thing is that in this case, because 60 and minus 60 are next to each other and minus 60 and 60 are next, D16 and D26 will also be a little bit less. We are talking about a group. So, the same group can be repeated. Another case, Case is plus minus 45, 0, 90. Okay. So, you have 4 layers, 0 degree layer, 90 degree layer, plus 45 degrees layer and minus 45 degree layer. So, here also we will get quasi-isotropy, but B will not be 0. So, if you want a symmetric B to be also 0, then what you do is you go to plus minus 45, 0, 90 symmetry, and what that will do is that B will be 0 and also D will be somewhat less. I mean, D will be less here also because there is a plus 45 sitting next to a minus 45, but the third thing you can do is, B is equal to 0. The third thing you can do is plus minus 45, 0, 90, 2 symmetric, and here D will become even less, and D16 goes down further because it is twice symmetric. Okay. So, this is how you achieve quasi-isotropy, but quasi-isotropy does not have to be symmetric, but if you have symmetry then B also becomes 0, which is an added advantage. So, this is what I wanted to discuss today in context of quasi-isotropy. Tomorrow we will actually do an example for quasi-isotropy, and in that example we will see how we can predict the Young's modulus of a randomly oriented fiber composite using this principle of quasi-isotropy. So, that is something we will discuss tomorrow, and then we will also discuss some other topics as well. So, thank you, and we will meet once again tomorrow. Thanks.